Their moon from Glotch.
From the moon to a moon, right? Or another moon. Yeah, so this is something that we just I started talking about doing this with Christopher Edwards last AGU, and we kind of been slowly moving in a direction of maybe coming up with some useful new observations and information. One thing that's really cool about Survey that I've been finding is kind of pushing a lot of us to kind of get outside of our comfort zones and tackle new, or at least new to me, problems. And so this has been kind of a fun project that we've been working on here. But first, I want to give a little bit of truth in advertising. This may be a little ambitious when we wrote the abstract. We're not quite there with the thermophysical model yet. We're working on trying to get a thermal model that is appropriate for Phobos, and I hope by maybe LPSC or something we can do this. All right, but let's move on. Here's the takeaway. This is, I think, kind of exciting. We observed with the thermal emission spectrometer a 6-micron water feature on Phobos, and this would appear to be in contrast to the apparent lack of a 3-micron water band in the visible near-infrared. We also have a tantalizing suggestion that at this point is still preliminary, but it's exciting, of a finely mixed secondary phase, which the best match so far is carbonate in the Phobos regolith. And then finally, a lot of people have talked about what types of products might be on the Phobos surface, and the data we've looked at so far, at least, are consistent with previous suggestions of phyllosilicates or desiccated phyllosilicates or shocked clays or something like that being present in the Phobos regolith. Before I get to the observations that we particularly made, though, I want to put them in context by talking about a lot of the previous work that's been done, starting with Murchie and Rivkin and Erard and Abby Freeman, who talked yesterday. So this is a plot from Rivkin et al. 2002, and what this is showing, this is summarizing lots of different data, dividing up Phobos into blue unit and red units that were defined by Murchie et al. But the takeaway here, the big point here, is that this 3-micron band, which we'd expect to be big if there was a lot of hydration on the Phobos surfaces, is weak or absent here. They constrained it to less than 5 or 10%, depending on whether you're on the blue unit or the red unit. This is in contrast to some of the spectral analogs that people talk about when they are talking about Phobos. A lot of the dark red asteroids, a lot of those things have hydration features that are there. So Phobos appears to be pretty dry according to this view here. Now, Abby Freeman gave a really nice talk yesterday, showing some more recent CRISM data. The takeaway there is, well, maybe after looking at CRISM data, Phobos is a little bit wetter, than we thought, based on just the previous telescopic observations. And we see this 2.8 micron feature. It's a metal OH band. It appears to be deeper in the red unit than in the blue unit. So, this could, form in situ. It could be an interaction of the solar wind, with the surface in a kind of like what's been discussed from in the moon based on M-cubed and other data sets. Abby and others also have shown that Phobos exhibits a weak but definitely present 0.65 micron band that has been attributed to things like desiccated iron-bearing clays or nanophase iron that scatters strongly and gives us a feature here. So this 0.6 micron feature could be clay, something else. What they don't see and what nobody has seen are strong or even weak 1 or 2 micron bands that would be consistent with the presence of pyroxene or olivine. In general, people in the past have talked about the best types of spectral analogs to Phobos being kind of red, low albedo asteroids, C, D, P, T-class asteroids. And in the lab, we can look at CM, CI chondrites, and those kind of look like Phobos too. Okay. And just 3 years ago, a group decided to look at the test data. Maybe there's something we can do looking in the thermal infrared. And so this group, Girana et al., looked at thermal emission spectrometer and European planetary Fourier spectrometer data. And they noticed that there's features here. So there's stuff that is interpretable. What you do with those interpretations is one thing, but they saw a silicate Chris-Johnson feature, which is the emissivity maximum that we see in silicates. And they see features that they interpreted as Rastral bands, major fundamental vibrational modes, and transparency features. They measured the position of the CF, and it's consistent with something that's ultramafic, low silica content. Now, lots of clays, feldspathoids have silica contents of 30-ish to 40-ish% silica. So we're not necessarily talking about ultramafic in the sense of having lots of olivine and pyroxene there, but low silica content. One thing that they noticed, one thing they discussed in their paper that was curious though, is that feldspars are the best match in the thermal infrared according to their data for the Phobos red unit. This would appear to be inconsistent with the visible near infrared results, which show this stronger 2.8 micron feature in the red unit. There's some, more clays. They see, CFs in general and spectral shapes consistent with phyllosilicates, except for in parts of the red unit. And so that's something curious we have to go back and look forward to. In general, I think that previous studies set up a lot of questions, and it taught us something new about Phobos. But Christopher and I, and eventually Neil Bowles and Carrie Delson-Hanna, thought we could wring a little bit more out of the data. So that's what we're trying to do here. This is an oldie but goodie thermal emission spectrometer. This was in orbit around Mars for like 9 years. It's a Mixing interferometer, measures temperature really well, and it's a hyperspectral instrument. So TESS and MGS were in orbit around Mars for 9 years, thousands and thousands of orbits. I've been looking at test data of Mars for better part of 15 years now. So kind of deciding to go look at Phobos with TESS is kind of like going home again. But it's different because it's Phobos. So it's like mom and dad turned my bedroom into a gym or something like that, right? But here's my great Photoshop skills. So we decided let's look at Phobos. Out of this 9-year mission, there were 4 orbits that we got data for Phobos, and out of those 4 orbits, there's one orbit, which we call OX. This is an orbit counter keeper with a close flyby of the daytime side. Let's see here. Okay, so we have several hundred observations from this one orbit. What we decided to do was down select to only observations with temperatures greater than 240 K. Within this orbit, the distance from the Phobos surface varied between 700-something kilometers and 200-something kilometers. Pointing and figuring out where each detector in the in TESS was pointing is really hard. And what we're kind of plotting here, just for a few observations, you can kind of think of those as like error ellipses, which we're going to reduce the size of over the coming months. We'll have better pointing and smaller fields of view here in the next few months. But figuring out which way TESS was going, whether it was upside down or right side up. There's some issues with the MGS aerobraking, so MGS ended up going in the opposite direction around Mars than we thought it was originally going to. So there's lots of issues that we had to figure out exactly where MGS was and how it was pointed when I was looking at Phobos. One thing to think about, though, is the true pointing is probably a bit different than was discussed or shown in the previous paper. Now, because we don't know exactly what the pointing was, we can tell if it was pointing on Phobos or it was half on Phobos, half off Phobos. We're only looking at observations that were completely on Phobos. There are 88 spectra with temperatures greater than 240 K. We haven't tried yet to divide them up into different units based on location because we're not sure of the location. So we just have these 88 spectra. We fit the radiant spectra with 3 black bodies of different temperatures to calibrate emissivity. This is almost exactly the way that Duran et al. Did it in 2011. If we get our 1 average spectrum, this is what it looks like. Now, the first thing you notice right away is that there are features there, and this doesn't look too bad. So we see emissivity minima here, and here, and we see overall relatively low 1 standard deviation. This gets higher out here, but this is a particular area of the spectrum that is very important to try to pay attention to and understand. So we try to wring as much out of this as we possibly can. And this is where we think we are getting some information. Now, just mention as well that the CF here is broad. It's centered at about 8.85 microns. The breadth of the CF probably is indicating mixing of higher CF and lower CF material, so more mafic, more silicic materials. And we also have to remember our experience with the Diviner lunar radiometer at the moon has taught us that space weathering shifts this back and forth quite a bit. So this ultramafic 8.85 micron CF, you know, if this is lunar-like, I'm not saying it's lunar-like at all, it could be shifted by 0.2 microns, you know, to more silicic, smaller, shorter wavelengths. Okay, but what I want to talk about is a region that hasn't been previously analyzed at all, which shows this kind of, you can't see, it kind of blocks this out here, this region over here. This hasn't been analyzed previously at all. What we see here is a roll-off in emissivity. This is very typical of finely particulate silicates, and it is something that we typically see. And we see this little bump here right at 6 microns that, if we believe that that's a real feature, is due to water. Now, this little bump here with these really big 1 sigma standard deviations is not too convincing, so the rest of this is trying to convince you that that's real, and then the structure here, which is important, is also real. And to do that, we use a technique that we've used a lot with the test data, mini-test data, called factor analysis and target transformation. This is a technique that's a principal components-based technique. We break up the data set into a set of orthogonal eigenvectors, and we map those back onto a set of target vectors. And if we get a good match, then we can say that our target spectrum is something like, is likely a component of the surface. So we can do this using a clay, clay spectrum. What we see is a very nice match in this portion of the spectrum, in the fine silicate roll-off portion of the spectrum, and especially over here at 6 microns. Not so good a match over here, but there's some kind of tantalizing, interesting features out here where we see not exactly the same, but something similar. And so if we look at this in a little bit more detail with more target vectors, we might be able to find a better match out here. But in general, a poor match out here. We also see, if we can look at a vacuum desiccated clay. In general, the fit is a little bit more poor, especially out here at shorter wavelengths. So we think, based on this technique, we have better evidence for a 6 micron feature here. Now, the other thing that we noticed is that typically, if you're looking at a finely particulate silicate, the emissivity rolls off, and there's not much going on out here at all. But we're seeing these bumps and wiggles. We see emissivity minima around here, and a maximum shoulder kind of right here. This looked really, really familiar, and this brought me back to my early days of graduate school when I worked on a paper with Josh Banfield, and we hypothesized and showed with some laboratory data that there are a few percent carbonate mixed in the Martian dust. And the basic idea here is that silicates have a very low absorption coefficient in this region of the spectrum. Other phases, like carbonates, have a very strong absorption coefficient, very high absorption coefficient. So when you mix them, you get intimate mixtures, you get nonlinear mixing. In this case, we're using nonlinear mixing to our advantage, and we are seeing just a few percent carbonate in the Martian dust. Now, the question is this also present on Phobos? We can do the same types of factor analysis and target transformation. I somehow found these spectra that I had taken, more than 10 years ago, off in an archive, and we see again a beautiful fit starting, somewhat to the short wavelength side of the Christensen feature. You see the fit going up here, which is due to the carbonate, going back down, which is due to the silicate roll-off, then going back up again, which is due to the 6 micron feature. With these 88 spectra and undivided and without any further processing, this is pretty good from a spectroscopist standpoint. I'm quite happy with this. Okay, so with that, I will just put up the summary slide here. These mid-IR data provide really important leverage in interpreting the composition and therefore perhaps the origin of Phobos. Okay, the test data show mid-IR stretching and bending modes between 10 and 20 microns. This is consistent with these types of silicate phases that others have talked about being present on the surface in the past. We see this broad, and I put ultramafic in quotes, CF at 8.85 microns. We have to understand a lot more about the space weathering environment at Phobos to understand what that means. We see this 6 micron fundamental vibrational mode indicative of water, and a short wavelength structure indicative of carbonate. Now, the interesting thing is here, people have talked a bit about D-type asteroids and such, and CM, CI chondrites as potential spectral analogs. This works in the mid-IR. Mean carbonate content in CM meteorites is 1.5 to 3%. That's easily within what we could detect with this technique here in the mid-IR. Tagish Lake, has 10%, tens of percent carbonate in it. So if it was a finely particulate, tens to 50 so micron regolith particle size, we should and there's 10% carbon there. We would expect to see it with tests, and I think we do. All right, that's it. Thank you very much.
Questions? Well, I have. Go ahead. I didn't see you back there. Carly Peters.
Well, actually, this may be the question you were going to ask. I actually have two questions. So, as I recall, the orbit is on the interior of Phobos, so you're looking at the Mars-facing part of. We
are looking at all these observations were done in the science phasing aerobraking orbit, right? So the orbit was changing a lot early on, and this is part of the reason that we're having a hard time tracking back down exactly where we're pointing. We know we're sitting at Phobos. We know we're around, those error ellipses that I showed. We know we're around Stickney. We're somewhere. Those observations that particularly showed are in the blue unit. We know we're on Phobos and where we're pointing. We just can't narrow it down to the 2-kilometer pixel size that we know we should have based on the distance.
Okay. Well, first of all, your spectra look wonderful. They're some of the nicest spectra I've seen for mid-IR of Phobos. The question I was going to raise, and I don't know enough about the TESS instrument, is whether you're seeing any Mars shine.
Yeah, that's a really good question. And that is something we will have to strongly consider, probably do some scattering modeling to figure that out.
Can I ask my second question?
Go ahead.
Did you see, I couldn't tell if any of those features were transparency features.
Yeah, so.
Which have to link with the regolith character.
Yep. So one thing that is interesting here, I'll just show this FATT spectrum. There's one thing that we see when we measure fine particulates in a simulated lunar or simulated Phobos environment is that for pure minerals that are finely particulate, we see very, very deep spectral features, low emissivities. We don't tend to see those on planetary surfaces, whether we're looking at the moon or Phobos. I think this is telling us something about the particle size. Okay, so the particle size is fine enough to have this silicate roll-off, but it might not be so fine that we're really into the regime of having transparency features rather than fundamental Westerolin bands. Okay. So I think we're going to. So these are, it's the old, this was the Salisbury paper where, the type 1, type 2, type 3, right? So we're kind of in that type 2, I think. We're not quite there yet, but I think this is something we'll be able to address a lot better once we get our thermal model up and running.
I have a question. If you have space weathering and you're altering things in the visible and near IR from silicate distorted lattice absorptions, and you take the iron out of those lattice positions, how does that affect the mid-IR?
So the mid-IR is, so the short answer to the question is we have a lot to learn about that, and that is one of the fundamental goals of the RISE team, right? So, but the mid-IR is sensitive to bulk silicate composition. We're much more sensitive to the silicate framework structure and what's going on with that than what's going on with, an iron in a M1 site or M2 site and whether that's getting poked out.
So if
things are turning glassy in the silicate structure, then yeah, we're going to see a huge difference. Okay.
Well, but if you lose the iron but you don't lose the overall structure, then you still see it. Is my point.
Yep.
Okay. That's cool.
One thing that's happening, though, like I said, we're seeing the CF shift back and forth, and this is kind of, we see this with Diviner, where it's very, very, on the moon, where it's very obvious, and it's not something we expected to see based on some experiments that were done in the 80s and 90s, and we are working towards understanding that. It's probably due to the thermal gradient and whether the darkening albedo is changing the thermal that we see with space weathering is changing the thermal gradient. These are hypotheses that we're actively working to test.
Okay. More questions? Well, thank the speaker and all the speakers for a great session. So we just have time to get back to the plenary session room. And